Sorry for the interruption. Okay, yeah. So let me do like a 10-second recap on this slide maybe. So now I was making the break. Okay, nice. So 10-second recap. We have a tensor category and a final function for this tensor category is Hopf algebra. So that this tensor category is the category of comodules with this Hopf algebra. I have there are some tensor category and final function hide a lot of technical assumptions. But for instance, look at CB. Well, C can be the category of representations of a finite group. It can be the category of algebraic representations of an algebraic group. It can be finite dimensional modules of a bialgebra and lots of other things. So usually what is exciting about the Tanaka reconstruction is that this category of representations contains enough information to remember H, our Hopf algebra. If we, of course, also remember the fiber function, otherwise, but for our purposes, I want to take a bit of a different, like opposite perspective, where what is nice about Tanaka reconstruction for this talk is that it repackages a lot of categorical information into a single algebraic structure. So it takes like a whole tensor category and just returns the Hopf algebra. And also those lengthy technical assumptions characterize categories which can be reconstructed in this way, so packed into an algebraic structure in this way. Okay. So I want to do something similar, like this kind of reconstruction, but instead of monoidal categories, I want module categories. So let me just introduce module categories really fast. So, okay, monoidal categories, one can view them as a categorification of the notion of the monoid. So a monoid is a set together with a function given a multiplication, which is associative and unique. A monoidal category, I replace my set with a category, I replace my function with a functor. My associativity condition with explicit associator isomorphisms, and there should also be a unit. I'd like to emphasize that the last property also in the case of monoidal category is a property and not structure. So, okay, what's a module category? Well, we have also the notion of a module over a monoid, also known as an act, which consists of a set, an action function, and associativity condition, and a unit of function. So now if I play the same game and I replace the set by a category, the function by a functor, the associativity condition by some associativity isomorphisms, and the unitality condition by unitality of isomorphism, I get a module category in some places also known as an actagon. So, okay. Where do they, how do they appear? So I'm a representation theory, so I care about the module categories here in representation theory. Well, if I have a representation from a group and I have a subgroup of this group, G, then rep G acts on rep H by just tensoring with the restriction. And this generalizes nicely to comodular algebras over general Hopf modules. Another example is if I look at modules over a finite dimensional semi-simple Lie algebra. I can form the so-called category O of some extra nice modules. I can form the category of finite dimensional module. That's kind of easier. And if I tensor something in category O with something in finite dimensional, I get something in category O. So this monoidal category of finite dimensional modules acts on category O by just tensoring. And now I can go a step further, split this monoidal category of finite dimensional modules with respect to this action. This gives me the notion of so-called projective functors, aka translation functors. And if I take this even a step further, this is in disguise the action of Zergel bimodules on Zergel modules of the co-invariant algebra. And so this kind of again is a common theme that I have an action of Zergel bimodules and Zergel modules. More generally, bimodules act on modules by things. So, for instance, I could consider Harish-Chandra bimodules associated with some Lie algebra, or just generally bimodules over an associative algebra, which is hence involving algebra. And okay, finally, another cool example is if we have an involution on a Lie algebra, then we can consider the action of the quantum enveloping algebra on the so-called quantum symmetric pair, or the high quantum. So this is how module categories appear in nature. but there is also a systematic construction which starts with an algebra object. So what's an algebra object? Well, okay, I have an object in my monoidal category. It needs a multiplication and a unit, which are encoded as a morphism from A tensor A to A, and a morphism from the monoidal unit to A, such that the usual commutative diagrams, which encode associativity of multiplication and unitality of multiplication, commute. And in terms of string diagrams, I can encode my multiplication as a nice little join, and those are the string diagrams, where the dotted diagram also, the dot encodes the unit. So that's an algebra object, but I also need the notion of a module object. So a module object is, so it's a very similar notion. If I have an algebra object A and C, I want an object M with C together with an action going from M tensor A to M. This really mimics the notion of a module. If C was vector spaces, this is literally on the nose, the notion of a module over an algebra. And I can again form this commutative diagram, these diagrams which are supposed to commute, and the string diagrams which also encode the same conditions. Where instead of a join, I should consider the merge of A into M. And then, if I have an algebra object, I can consider the category of all right module objects over A. And this is a C module category. So the slogan being categories of modules are module categories. The observation is just that I can tensor and write a module with anything from the left. And there is a natural action which just acts on M, does nothing on V. It's in the case of C being vector spaces, it's just tensoring a module with a vector space. This generalizes as construction, and in terms of string diagrams, it's also very natural. I want to define a join into V tensor M. Well, V tensor M can be represented by a pair of parallel strings, one for V and one for M, and I just join into M. As an example, well, in fact, we've already seen an example of a module category of this form. So we saw that if I have a finite group G and a subgroup thereof H, then the rep G acts on rep H by tensoring with the restriction. And in fact, I can find an algebra object in rep G so that this module category is the category of modules for that algebra object. In this case, is the dual of the permutation representation on the set of cosets G mod H. So those module categories are equivalent. But the more interesting direction is when module categories are categories of modules. So in other words, given a module category, can we find an algebra object so that this module category is the category of modules for this algebra object? The idea being that, okay, we have a lot of categorical information and we repackage it into a single algebraic structure internal to this monoidal category that we started with. And second, we would like to characterize it for which module categories this is possible. So in that sense, this is very analogous to the Tanaka reconstruction when I'm viewed it in the correctness. Okay, if we can find an algebra object like this, we say that we have kind of reconstructed our module category. And the main result in this direction for finite tensor categories, meaning a tensor category with finitely many simple objects, is the result of Ostrik, and then, okay, Ostrik in the semi-simple case, and then it's Ostrik in the general case, where if we have a finite tensor category acting on a finite C module category, and this module category has an internal projective generator, I will not go into detail on what exactly that means, then this module category is the category of modules, and the algebra object is just the internal endomorphism algebra for my internal generator. I'm doing Morita theory and I'm throwing in the word internal in many places, essentially. So I take the internal home from X to X, where X is this generator. So that's the case of finite tensor categories, and can be rephrased also as kind of reframing module categories of internal Morita theory. because finite module categories up to equivalence, studying finite module categories up to equivalence then becomes the same as studying algebra objects in C up to Morita. So the Morita theory kind of internal to C. And this can be rephrased nicely in terms of Hopf algebras. So in the special case where C is just comodules over some Hopf algebra, then these module categories can be described in terms of comodule algebras up to suitable Morita. But okay, this is finite tensor categories, and a lot of categories already in the example from examples from previous slides were not finite tensor categories. So what do we do if we have some monoidal category which is in some way more complicated, or if we have a module category which is in some way more complicated? For instance, what can happen is that C is infinite, meaning okay, it's still a tensor category, it still satisfies those 7 assumptions or whatever I had on the first slide, but there's infinitely many symbols. But the fact that there is still enough projectors, this doesn't happen too often, but it happens, for instance, for finite dimensional modules over nice Lie superalgebras. This is one of the cases that was studied by Ostrik, and another case that also doesn't satisfy or doesn't fit into the finite tensor category setup is the case of categorical actions of certain bimodules, where the categories that we studied are, in a very strong sense, finite, but they are not acute. So they are additive categories. There is finitely many decomposables, the home spaces are finite dimensional, there's all kinds of finiteness conditions one can ask for, and they will be satisfied in this setup. But those categories are not. So what happens then is that there is still an algebra object using which we can reconstruct our module category, but it no longer necessarily lives in C itself. So in both those cases, in fact, it lives in a suitable co-completion of C. So in the first case, one should consider int objects, so the incompletion, and in the latter case, it's the finite co-completion, which consists of formal projected presentations over C. In the latter case, it kind of mirrors the idea that we want to assign some abelian category. We view our category that we started with as projective objects in some category. So, being as we can solve problems in representation theory and in Hopf algebras by moving to algebra objects in a different category, this gives us a different perspective on this problem. So we can reformulate the problem as finding a new monoidal category D of C, so that the module categories over C is internal Morita theory for D of C. So it's kind of shifting goalposts, but it's pretty useful. We saw in the previous slide that if there are some finiteness, non-abelianness issues, then D of C should be some nice co-completion of C. And yeah, there is the notation D of C is not completely coincidental. There is a relation to the infinite center. Maybe not go into the details on that right now. So there is one more question that I want to pose before stating the result, which is what happens if C is not rigid. So in the cases that we've considered so far, if we have finite dimensional comodules over some Hopf algebra, we have zergal bimodules, we always have the notion of a dual object. So for a Hopf algebra, if I have a representation of a Hopf algebra, I can take the dual representation. For the zergal bimodules, it's as obvious, but if we have a hot Samuelson bimodule, we can take the dual itself. So for more formally speaking, for all objects V in C, there is an object V dual, so that tensoring with V and tensoring with V dual is an adjoint pair of functions. This is being a right dual, so V third is right dual here. Again, we say that the category is rigid if you have both right and left duals. So there's plenty of categories that are monoidal but aren't rigid. And the first example is the first monoidal category on C, most likely, which is the category of sets, or finite sets also works. The only category that admits a dual, the only object that admits a dual in set is the symbol. It's self-dual. Because if one plays with the home junctions, one gets an equation that is only satisfied But okay, more representation theoretically, we can consider representations of monoids that are in groups. This will not have duals for all objects. Some objects will have duals, but not all. More generally, we could take a bialgebra, which is not a Hopf. In particular, a semi-group algebra would work. If we want to be a bit fancy, we can take G crystals for a semi-simple algebra. Or, okay, another topological case is we could take all modules over a Hopf algebra, and then the infinite dimensional ones do not have nice notion of G. So the question is then, can we reconstruct module categories also in the non-rigid case? And so the answer is that under some assumptions, we can. So with no assumptions on finiteness or existence of geos, there is a monoidal category, D or C, so that if we study module categories with an internal additive generator, this is where we kind of throw in a bit of a strong assumption to compensate for the lack of assumptions above us. Those always give rise to algebra objects, and equivalence corresponds to Morita equivalence. Module functors correspond to nice bimodule objects. So functors given the tensor with the bimodule. Better yet, we have a meaningful interpretation of a general bimodule object, which doesn't necessarily yield a module functor. So it yields something slightly weaker. It's still a functor, but it doesn't satisfy the properties well that need to have to call it a module. And furthermore, this extends to two morphisms as well. So this is a full-fledged biequivalence. It's a two-category equivalence. So okay, the question is, what is DFC, right? So in the setting of this slide, I guess I should say that DFC is the weak C module endomorphisms of the right regular module. Weak C module morphisms in the sense of the second line, third and fourth. But those are precisely Tambara modules on C, and that's why Tambara reconstruction. So before I start talking about Tambara modules, let me say a few words about the rigid case. So how does the reconstruction work? How does this algebra, how do we get an algebra object? Well, so let's start with some nice monoidal categories, say tensor category, acting on some nice module category with a generated X, and how do we get an algebra object? Well, when you look at the pre-shift, that takes something in my category C and sends it to C acts on X to X, like the home space from C acts on X to X. And in the setup of etching of Ostrik, we observe that this is left exact. So this is represented by some object in indoor C, and then we just using composition of morphisms and some yoga of adjunctions, because there is a lot of adjunctions flying around, prove that this is an algebra object, and then prove that the modules for that are the modules for the corresponding monad given by tensoring with this algebra object, and then use the parameters. So then we can put it into a big categorical machine and we get parameters. In the case of non-abelian actions like those of Zerga line modules, we again study the same pre-sheet. This time we use the fact that it's finite dimensional and that my category C is kind of even smaller than it was in the previous setting. So then this will be represented by an object in the finite for completion. Again, we prove that this is an algebra object by some convoluted yoga of adjunctions. And then there are two papers which don't really study this reconstruction process as their main objective, but they take a slightly different route. Namely, they look at this action functor, which takes my generator and acts on it, so it's a functor from C to M. Then we observe that this is the right adjoint because of our finiteness assumptions. And then we say, okay, this is the right adjoint, let's compose the two, we get a monad, and now we do Barbeck on this. So again, we just reduce this to the monadicity theorem, aka Barbeck. And seemingly this is very similar. But in the non-rigid case, this is very different. And this works. So the first approach is like, first we get an object and then we prove that it's an algebra object, so we get a monad. The second approach is like, first we get a monad and then we show that it's also an object in some code conditions. So let's see why this first approach doesn't work. So let S be a monad. let be maybe a finite monoid to make it a bit simpler, and take let R be a congruence on S. So an equivalence relation is suitably compatible with the multiplication, so that I can form a quotient S mod R, and this is still a mod. Then the category of S graded finite dimensional vector spaces acts on S mod R graded finite dimensional vector spaces. And this action, in order to specify it, I will need to specify what I'm doing on one-dimensional spaces concentrated in a single degree. So I look at one dimensional delta subscript superscript here denotes the one-dimensional space concentrated at element subscript in the monoid superscript. So this is my action, and delta 1 S mod R is a generator for this action under any definition of a generator you will find in the literature, like in super strong sense. So then let's look at that presheet that Ostrik or Mateusz Stroiński will study and see what kind of values it takes. So again, we only need to evaluate it at a one-dimensional space concentrated at some element in my monoid, and we see that this is non-zero if and only if P is congruent to 1. What's the problem with this? Well, the problem is that this does not distinguish congruences whose congruence class of 1 is the same. Right? So for congruences or groups are given by normal subgroups. Like congruences are just like modding out by a normal subgroup, and then we have the Lagrange theorem, telling us that if I know one coset, I know kind of all of them, right? They're all of equal cardinality. Here I can have a more general congruence, or a pair of more general congruences, which agree on the class of 1, but don't agree in general. And this does not distinguish between them. And so one can easily cook up some pair of congruences, for instance, on the additive monoid of natural numbers, so that they agree on 1, but they give me non-equivalent module vectors. So this tells me that the Ostrik construction kind of fails, right? It takes two different module categories and it gives me the same algebra object. So it's not a complete invalid. On the other hand, if we allowed, instead of the presheet, if we allowed two inputs, one on the left-hand side and one on the right-hand side, and we see what happens if I evaluate at the one-dimensional concentrated at T and the one-dimensional concentrated at U. This is non-zero if and only if T is congruent to U. And this kind of clearly recovers all the information I need about this congruence. This literally recovers the equivalence relation. So it seems like we need two inputs. Why does this? Okay, so why does the one-sided approach magically work in the rigid case? Because I can act by, say, W dual tensor V, and this is all from Vx to Wx. So this leads us to the definition of a Tambara module. So the Tambara module takes two inputs. It takes a contravariant input, it takes a covariant input. In C, it returns a vector space. It also has requires some structure maps from, say, phi UV to phi T tensor U, T tensor V, so it's like tensor unity. And then some exceptions. Quite natural exceptions. What is the relation of that to reconstruction? Well, we want the Tambara module, which takes UV and sends it to the home space from U acts on X to V acts on X. So the exact thing that we saw in the previous. And the structure maps are simply tensoring or acting by T, then filling in some coherence isomorphisms and all that is structure map. It's very easy to find. Then what is not so easy is convincing oneself that one can in a meaningful way tensor Tambara modules so that the category of Tambara modules is monoidal and that this defines an algebra object. But once you know how to tensor Tambara modules, seeing that this is an algebra object is super easy. And this is the algebra object, which in this reconstruction result corresponds to M. Okay, so this is a whole lot of abstract nonsense. So this is a more concrete case. So let's look at some bialgebra B, and let's see the category of finite dimensional comodules over B. Consider some nice module category M over this, and we obtain a left exact lax C module monad, which is supposed to be somewhere on this slide, but I'm not finding it. So we obtain a left exact lax C module monad from this two-sided construction, because we can identify Tambara modules with some nice Python module via the Eilenberg-Watts. And then we show together with Tony Zorman, this is a work in progress. So essentially, this half of this last 4 minutes of this talk is joined with Tony Zorman, and so in preparation. So what we show is that lax module and the functors correspond to Hopf trimodules, like something that's a bipole structure and a module structure in a compatible way. And the correspondence is quite natural. Either from the left-hand side to the right-hand side, we evaluate B. From the right-hand side to the left-hand side, we take the cotensor product with X. And crucial in this is Eilenberg-Watts calculus, a lot of operations or manipulations on string diagrams, and this idea of a Jeter-Dinfeld braiding, which tells us the lax C module structure on this functor. So a lax C module structure consists of precisely maps like this, and this is them given a dimensional X. So we can make this more complete. If B is a semi-group algebra, then a Hopf trimodule is just a S-bigraded S module, and an algebra object in that is just an S-bigraded S module algebra. And then, okay, I think I will skip over this, but the point is that if one looks at the semi-group on two elements, which is not a group, but it's non-trivial, and looks at semi-simple module categories of this. So this is very similar to what one would do for tensor categories. You look at semi-simple module categories where you're semi-simple tensor category. And in this case, this semi-group algebra is this semi-group algebra is semi-simple. One can characterize indecomposable semi-simple module categories. Both act on vector spaces. The only thing that distinguishes them is the action of the one-dimensional concentrated in degree 1. And the associated trimodule algebras distinguish the two indecomposables very clearly, but the usual approach would actually confuse one of the indecomposables with the regular representation, which is not indecomposable. So this is a kind of explicit example where we just have very low dimensions of home spaces, low number of simple objects, where we see that the usual construction doesn't work, and this construction gives a complete classification on the notes. Okay, so let me just skim over some applications. So surprisingly, using this machinery, we can generalize the theorem of Ostrik and Ostrik on the reconstruction for C module categories where C is a tensor category. So that theorem assumed that C was a finite tensor category. What we can do is we can drop the assumption that it's finite. Because we use a lot of stuff on injective objects in the incompletion of this tensor category. And instead of algebra objects, we recover co-algebra objects. So it's a bit more like the theory of co-algebras also. And the other application we have is if we consider, again, this correspondence between C module categories with a projective generator and algebra objects in C for a finite tensor category, we can show that exact C module categories match with simple algebra objects, where this is actually a mistake, I should say semi-simple algebra objects. So the way we do this is we introduce a notion of a radical for a category of modules for an algebra object. And lastly, I wanted to kind of emphasize that this whole Tambara setup could be deduced from the results previously known in the literature, but I think I'm skip that, and that's all I have to say. Thank you.
Question. It replaces your Tambara modules in terms of program, as long as program is.
Yes, a Tambara module is a lax module for yes, it's a lax module.
Module program are always lax, but this is strong module.
What is the strong module? Well, I mean, the strong module factor would have its action maps invertible. This is kind of very rare, but
It's very rare.
yes.
Is the category ESC, did you tell us what a weak module was?
Yes, it's a Tambara module. It's
Yeah,
exactly
but
the
so this ESC, is it, I guess even from the descriptions, is it clear that it's a graded model?
It's a graded monoidal. It will not be graded monoidal unless, okay. There is no good reason for it to be graded monoidal unless it was graded monoidal. If C is graded monoidal, then I think it, but I am not 100% sure.
I mean, I guess I seem to remember people looking for examples of categories where the category of algebras has this monoidal structure, but the category itself is not very monoidal. So does this produce examples of something?
I cannot speculate.
So this DFC is in the billion.
Yes, even if C is not a given, then D of C is a given. Yeah.
And this indicates that D of C is a log of D of C.
D of C is a very risky proposition because it's I mean D of C is already not like as small as so you will get small issues like maybe if C is finite symmetry or something like finite, very finite.
Same thing, D of C is finite tensor category that the D of C is equivalent to C, right?
If you frame things correctly, then yes. Like you need to do it modify. If you only allow the parameters that are finite dimensional on all pairs of edges, then yes. Otherwise, no.
No more questions, then let's speak again.